Okay, next speaker is Victor Mishnyakov from NORDITA, and he'll talk about the Coulomb branch of N=4 and integrability.
Okay, thanks for the introduction. I'd like to thank the organizers for putting up this conference and giving me the opportunity to present my work. So I'm going to talk about some work that is based on this paper and related to the Coulomb branch of N=4 super Young-Mills theory. So let me start with a few introductory comments. So super Young-Mills theory has many nice features, some of which were highlighted and will be highlighted at this conference as well. So such as integrability, holography, and many others. And these are reasonably well understood at the conformal point, or in other words, super Young-Mills theory as a conformal field theory. What we are interested in is to study this theory in a symmetry breaking vacuum, so in scenarios where conformal symmetry is broken. And well, there are actually many examples of such scenarios, and quite often they lead to defect CFTs, which we also heard about. In our case, the symmetry breaking pattern is going to be a bit different. It's not going to lead to any specific defect theory. So let me just explain the setup straight away. So in the gauge theory, we have the scalar fields of super Young-Mills theory, which can be given a vacuum expectation value based on the shape of the potential. And a very simple way to give a VAV to the scalar fields is to choose the following classical solution, where we only have one non-zero matrix element of for these fields. And well, while of course everything is rotationally invariant, it's sometimes useful to just choose this vector to stick in one specific direction. So some of the formulas will use this. Oh. Okay, so, well, by giving this expectation value to the scalar fields, we break conformal symmetry, but conformal symmetry is broken in a sort of homogeneous way. So it's broken to Poincare symmetry. So there's, contrary to the defect scenarios, there's no residual symmetry in any direction, but there's also no preferred direction. And then the gauge symmetry is Higgs, of course, where this gives us a bunch of massive fields from the fields with indices 1j. So, but for j not equal to 1, because this 1, 1 slot actually is responsible for this U1 factor over here. So in the holographic picture, in the dual picture, this scenario corresponds to taking one of the D3 branes in the stack and moving it away at a certain distance. And well, it's going to be positioned in the ADS space, a coordinate that is related to the vacuum expectation value, which we can sort of compute by equating the tension of the strings that can now extend from the brane stack to this probe brane to the mass of the W boson, so to the massive particles. So this scenario is interesting for a few reasons. One is, of course, just to study holography and integrability beyond conformal symmetry. So it's broken here. This is the same motivation, for example, that appears in the study of the defect scenarios. Also, this theory is kind of closer to realistic ones because it has massive particles, broken conformal symmetry, and has nice properties in terms of its spectrum and the S matrix. And then the most natural objects to study in such scenarios are one-point functions of operators or condensates, and these are also important objects in QCD, for instance. So although, of course, this scenario will not give any immediate consequences for QCD sum rules, it's still interesting to study. So one of the main things to do is to compute one-point functions of operators. And that's what I'm going to talk about partially. So there are two kind of distinct cases. So first are the protected operators, for example, the scalar chiral primaries. So these are not particularly interesting in a sense. They are tree-level exact. Well, they are protected, so they don't renormalize, but also their one-point functions turn out to not have any loop corrections. And well, they also coincide with the holographic computation, which I don't present here, but it's a pretty standard. It's pretty similar to the standard holographic computation, except that the gravitational action is modified by adding the D3 brain action, the probe brain action. So since it doesn't receive any loop corrections, it means that basically the one-point function corresponds to substituting the field with its vacuum expectation value. So other operators that are non-protected, they receive loop corrections, which is kind of richer. So I'll present everything using the example of the Konishi operator, this one. And so since we know that these operators are renormalized by themselves, it's important to include the normalization factor. And when we compute their one-point functions, we need to deal with this renormalization. And there are two, I guess, most important things to consider. So first of all is the question of the finiteness of these one-point functions. And interestingly enough, it happens so that there's no extra renormalization coming from the one-point function. All the divergences can be accounted for by renormalizing the operator at the conformal point. This is, well, I don't know if this is a theorem, but I guess, well, at least in this case it's true, but probably also in other scenarios with spontaneously broken conformal symmetries, contrary to, for example, breaking conformal symmetry by just adding mass explicitly. So the other question is scheme dependence. Since we want to extract the finite parts of these loop corrections, and these are often scheme dependent since we will renormalize things. And we want to extend these loop computations to such things as integrability, for example. And of course, therefore, we want a scheme independent result. And it turns out that to deal with all these problems, it's useful to define the renormalized one-point function in the following way, where we compute the vacuum expectation value on the Coulomb branch of the Baire operator, and then we divide by this factor, which is computed, as you can see here, there's no V subscript, so it's computed at the conformal point, which means that the X dependence is cancelled by this prefactor here. And this expression turns out to be finite, but also it's explicitly scheme independent. Because, well, at least within multiplicative renormalization, whatever renormalization factor you add is going to cancel here. So we compute this, and, well, this is the result we get at one loop. And it's better to present it in the following way, where we kind of take into account the dimensions of this operator. So we have V to the delta K, where delta K is the anomalous dimension to one loop, and then CK is kind of the kinematic data here. So this is just the result of a one loop computation. Interestingly enough, there is this Euler gamma factor over here, which kind of typically appears as a scheme-dependent contribution in loop computations. But this, as I said, this result is scheme-independent, and in fact, this gamma factor is later reproduced by integrability. So the first hint of integrability at loop level is that, well, now in general, expectation values of operators to one loop can be presented as an overlap of the in the spin chain language, it can be represented as an overlap of the state corresponding to the operator with a boundary state. And this boundary state turns out to be integrable. So it's annihilated by an infinite number of conserved charges. So, well, one-point functions are not the only interesting object. And we also did study two-point functions a little bit. And the two questions that one can address here is the short and long distance expansions. So for the short distance expansions, it's interesting to study the OPE and the relation between the OPE and the vacuum expectation values. So if we take, for example, this simple BPS operator, Z squared, and then consider the following OPE expansion, then we expect to see contributions of the following operator, well, the identity, this O tilde is another BPS operator, and then the Konishi. So interestingly enough, for example, So now we're going to take the expectation value of this expression, and since we're in a Coulomb branch, this left-hand side will not be trivial. It will contain all the one-point functions of all these operators. And interestingly enough, we have parts here that correspond to operators that are not renormalized and to those that are renormalized. Well, obviously, the two-point functions have loop corrections, even though the operators are not renormalized. But anyway, it's an interesting interplay. So when we take the expectation value at the leading order, we compute the following diagrams. Something which is not drawn here is that in this middle diagram, due to the way counting works in this vacuum, this diagram over here contains a massless propagator, but this contains the massive propagators. So this is the kind of interesting part, which is, well, specific to the Coulomb branch. So when we do this simple computation, well, we expand the massive propagator to a few first orders. We need also the structure constants, which I did not write explicitly here. We need them to one loop order. And then if we write out the result of computing this two-point functions and contrast that to the OPE, we find that the consistency of this expression requires that the following equation holds. So here I specifically wrote it in a way as if we don't know these quantities to kind of illustrate that the consistency conditions require that the one-point function of the Coulomb branch requires well, a specific value. So it can be thought of as an equation where we compute some of the quantities and then determine the rest via this consistency. And funnily enough, actually, to find the anomalous dimension, we don't even need the structure constants to one loop. We just need the massive propagator, since this diagram is just a square of the massive propagator. So we kind of compute something that is one loop without computing any loop integrals. But this is an interesting observation. So by analyzing these expressions, we find that one loop corrections do not spoil the convergence of the OPE, well, at least in this sense where we evaluate the OPE in this vacuum. And this motivates to, well, to think about this idea of a kind of Coulomb branch bootstrap, or maybe called something else, where we can consider two regimes of our two-point functions. One is the short distance expansion, which gives the OP, and then we can sort of predict the structure of the long distance expansion, something that will also appear in the next slide. And then comparing this expression, equating them, we can set up equations on this OPE, on the CFT data. So we can kind of figure out what conditions on the CFT data can allow Coulomb branches. And so one exercise that we did is a crude estimation of how the OPE data should grow. And then in this paper, it was shown more specific examples were considered, and what they got was actually in agreement with this estimation. So at large distance, well, something that we can check in this scenario is something called the dilaton word identity. So, well, since we have spontaneously broken conformal symmetry, we expect a dilaton. And in fact, we can predict on general grounds what the contribution of the dilaton should look like. So it's this part over here. So the power law behavior at large distances can be predicted. And, well, this should hold in principle at any loop. And something that we managed to see, that this constant over here, which is kind of the characteristic of this dilaton decay constant, it's not renormalized at one loop at least. So this can be in principle kind of further studied in this scenario. So going back to integrability, well, integrability of super Yang-Mills itself has different incarnations. It can be shown that, well, there's a spin chain description at the loop order, which can be extended to any value of the coupling via such approaches as the quantum spectral curve. Then there's the string sigma model, which is also integrable. And well, to show integrability on the Coulomb branch, one has to kind of show, one has to go through all of these. And so these were actually shown in a few subsequent papers by some of my co-authors and their co-authors. So integrability at it was shown that this overlap formula with integrable boundary state can be extended to generic coupling up to Sankavitz by Coronado, Komatsu, and Zarembo. And then the string sigma model with this bulk D3 brane was shown to be also integrable in this paper. And then something that I didn't mention yet is that one can study amplitudes or deformation of super Yang-Mills amplitudes to the Coulomb branch, and it turns out that these also have some integral properties. Mainly, they retain some of the dual conformal and Youngian symmetry of the super Yang-Mills amplitudes. So just to recap, so it's safe to say that this Coulomb branch configuration is integrable. It has many interesting implications. So it would be interesting to study other observables. And in particular, it would be interesting to address this other question that I highlighted about the relation of OPE and condensates, and maybe within this integrable framework. And then something that I did not talk about, but well, it's in the paper, is the relation of this Coulomb branch configuration to large charge operators. So this is something that I'm not going to touch. Yes, thank you.
Thank you. Questions? There's one. Yeah.
So the coefficient for the 1-point function that you had, the CK, this
Yes, sorry.
the one loop. Do you know what's the behavior of that coefficient at strong coupling? You know, from a string theory argument, do you know? Is it lambda to some power or?
I couldn't say at the moment, I think, but yeah, I can look it up and yeah, let you know.
Well, going back to the 2-point function that you showed expanded in OPE, like, are there any properties of the 2-point functions that are not enjoyed manifestly by the OPE, which could then be leveraged for Bootstrap?
Properties of the 2-point function, which
For
are
example, at finite temperature, the 2-point function would be periodic. The OPE itself is not. Every term is not periodic, but you can use this as a consistency condition.
Well, I would say, for example, the statement about the convergence of the OP can be studied by looking at the properties of the, because you have a kind of exact result, and you know, well, in this case, it's just like Bessel functions squared, and you know that they have an infinite radius of convergence, for example, and you also know the structure of their large X behavior, for example. So you can, from the short distance expansion, you wouldn't be able to tell immediately, and that's basically how you can set up this kind of bootstrap equations.
Okay, thank you.
Can you say more about the holographic computation, which you can check the full protected sector?
Well, we checked the chiral primary operators, and well, the computation goes pretty straightforward. So you simply modify the gravitational action by adding a D3 brane action, and then you do the same computation you would do for the conformal point. And so, well, yeah. The only difference being that now you are computing a 1-point function, which in principle you wouldn't do on the conformal point because it would be 0. Yeah.
Okay, if there's no more question, let's thank Victor again.